In October 1973, the skies over the Sinai Peninsula became the most dangerous airspace on Earth. The war that erupted between Arab coalition forces and Israel was, among other things, the first large-scale test of modern surface-to-air missile systems against a sophisticated Western-equipped Air Force, and the results shocked every military establishment that was paying attention. Israeli aircraft, among the most capable in the world, and flown by pilots with exceptional training, were being destroyed in numbers that no one had predicted. The Soviet-supplied air defense network that Egypt and Syria had deployed was performing at levels that Western analysts had not believed possible from available intelligence. The lessons that military planners drew from that conflict were numerous, and some of them were contradictory. But one lesson was universal and unambiguous. Air defense technology had reached a level of maturity where it could genuinely threaten even the best combat aviation. And the air forces that did not take this seriously would pay for the oversight in aircraft and pilots. What the planners on both sides also understood was that the specific systems that had performed so effectively in 1973 were already being studied, analyzed, and countered. The window of advantage that any particular air defense system enjoyed was finite, and the next generation of threats, lower flying, faster reacting, better able to exploit the gaps and blind spots of current systems, was already in development. In Moscow, the engineers and military planners who reviewed the 1973 conflict data were looking at this problem from a specific angle. The existing Soviet air defense systems had performed well against medium and high-altitude targets. They had been less effective against aircraft flying at very low altitude, exploiting ground clutter to mask their radar returns and terrain features to complicate the geometry of the intercept. And the trend in Western offensive aviation was clearly moving toward exactly this threat profile. Aircraft designed to fly at extremely low altitude, following terrain contours, staying below the effective engagement envelope of existing missile systems. The system that had been the most recent Soviet response to low-altitude threats had entered service only 2 years before the 1973 conflict. It was mobile, capable in its designed role, and represented a genuine step forward from what had preceded it. But the engineers who had built it were already aware of its limitations before it reached the troops, and the 1973 data confirmed what they had expected. The threat was moving faster than the solution. What was needed was not an upgrade of the existing approach, but a fundamentally different architecture. The discussions that began in the early 1970s in the research institutes responsible for Soviet air defense development were characterized by an unusual combination of ambition and technical honesty. The engineers involved knew what the next generation of threats would look like. Cruise missiles flying at very low altitude, unmanned reconnaissance platforms operating at medium altitude for extended periods, combat aircraft with increasingly sophisticated electronic warfare capabilities that could suppress or deceive existing radar systems. They knew what they wanted to build to counter these threats. And they were honest about the fact that several of the technologies required to build it did not yet exist in the form that the concept demanded. The central technological challenge was radar. The concept called for a system in which all the functions, target search and detection, target tracking and identification, missile guidance, would be performed by a single integrated radar on a single vehicle. No separate command posts, no remote radar stations connected by cables. One machine that found the target, kept track of it, launched a missile, and guided that missile to intercept, all through its own organic systems, all within the response time that the anticipated threats would require. Achieving this with the radar technology of the early 1970s was not straightforwardly possible. The specific radar approach that would make it work, a phased array antenna that could electronically steer its beam without mechanical movement, interrogating multiple targets and tracking multiple objects simultaneously by switching between them faster than any mechanical system could rotate, existed in large-scale applications. The Soviet Strategic Defense Network used phased array radars of extraordinary size and capability. But taking that technology and reducing it to something compact enough to fit in the turret of a tracked fighting vehicle, while preserving its fundamental capabilities, was an engineering problem without an existing solution. The response to this situation was unusual and, in retrospect, clearly correct. Rather than attempting to force the development of a system with technology that was not yet ready, the program leadership took a deliberate 3-year pause, using the time to advance the relevant technologies to the point where the concept was actually achievable. This kind of institutional patience, accepting a delay in capability in order to ensure that the capability, when it arrived, would actually work, was not common in any military development establishment, and the decision to take it reflected both confidence in the overall concept and realism about what rushing the technology would produce. The pause was used productively. Engineers worked on miniaturizing the phased array technology. They worked on the digital processing systems that would be required to handle the data flow from a radar simultaneously tracking multiple targets and guiding missiles. They worked on the specific problem of vertical launch, the concept that missiles would be ejected straight upward from their containers and then steered toward their targets in the air, allowing the system to engage threats from any direction without the delay of traversing a conventional launcher. And they worked on making all of this fit inside a tracked vehicle that could keep pace with armored formations moving cross-country in any weather. The formal development program that began in 1975 assembled a team of designers with exactly the combination of experience the project required. The chief designer had previously led the development of a successful medium-range surface-to-air system that had performed well in operational service, giving him both the technical knowledge and the institutional authority to manage a program of this complexity. The designer responsible for the combat vehicle had worked on multiple previous systems in the same class. The design bureau responsible for the missile had a long record of successful weapon development across several generations of Soviet air defense systems. The missile problem was among the most technically demanding aspects of the entire program. The weapon had to be compact enough to fit 8 rounds in the space available on the vehicle. It had to survive the vertical launch sequence, the initial catapult ejection that would accelerate it from rest to a launch velocity using a pyrotechnic charge, followed by a transition phase in the air during which the folded fins would deploy. The rocket motor would ignite, and the missile would orient itself toward the target. The folded fins were necessary because a missile with fully extended fins could not fit in the container. They had to deploy reliably in the airflow immediately after launch, and the deployment mechanism had to work every time, in any weather, at any temperature, because a deployment failure meant a missile that could not be guided and could fall back onto the launching vehicle. The guidance approach added further complexity. The same phased array that searched for targets and tracked them would also guide the launched missile. Switching between its roles of target tracking and missile command transmission fast enough that neither function was meaningfully degraded by sharing antenna time with the other. The electronic scanning capability that made phased arrays superior to mechanically steered antennas for this kind of multitasking was exactly what made the technology essential to the concept, and exactly what made the technology difficult to miniaturize. The development took 8 years. The prototype that emerged in 1983 and was taken to a test range for initial trials represented a decade of work by hundreds of engineers and thousands of technicians. And the results of those initial trials were not satisfying. The electronics were unreliable. The vertical launch worked inconsistently. The missile's propulsion showed unpredictable behavior. The guidance system did not achieve the accuracy that the specification required. The radar's performance against small targets, specifically the cruise missiles and unmanned vehicles that were the primary rationale for the entire program, was not at the level that operational use demanded. The Evaluation Commission produced a report that listed the deficiencies systematically and sent the entire system back for remediation. Another year of intensive work followed. Engineers traced fault after fault, redesigned problematic subsystems, retested components that had been causing failures, and gradually worked through the list of deficiencies that the initial trials had identified. When the updated system returned to the test range in late 1985, the results were categorically different. Missiles left their containers consistently and reliably. The vertical launch transition, the critical sequence of fin deployment, motor ignition, and target orientation, worked as designed. The guidance system tracked its assigned targets, and the missiles hit them at the probabilities the specification had called for. In March 1986, 14 years after the first discussions about what it might look like, the system was formally accepted into Soviet military service. The fundamental operating sequence that the system used in combat was a direct realization of the concept that had been described in those early 1970s discussions. Deployment from march to combat readiness took approximately 3 minutes, the time required to raise the search radar antenna from its transit position, bring all systems to operational state, and complete the initialization sequence. Once deployed, the search radar rotated continuously, scanning the airspace in all directions to a range of approximately 27 kilometers, producing a picture of every airborne object in the protected area that was refreshed fast enough to track even fast-moving targets. The identification system ran alongside the search function, determining whether each detected object was a recognized friendly aircraft or a potential threat. When a suspicious contact was confirmed, the tracking system, the phased array that formed the core of the guidance capability, took over, locking onto the target and beginning the continuous measurement of its position in 3 dimensions that the guidance calculation required. The onboard computer processed this information, classified the target type based on its flight profile and radar characteristics, and selected the guidance algorithm most appropriate for what it was tracking. A high-altitude fast jet required a different intercept geometry than a low-altitude cruise missile flying at terrain height, and a hovering helicopter required different solutions than either. The launch sequence itself was the engineering achievement that most clearly distinguished this system from its predecessors. The catapult fired. The missile accelerated upward from its container in approximately a fraction of a second, reaching a velocity of roughly 25 meters per second by the time it cleared the launcher. At approximately 20 meters above the vehicle, the onboard autopilot received the initial targeting data that had been loaded at the moment of launch, calculated the required orientation, and deflected the control surfaces. The missile pivoted in the air, pointing itself toward the target. The folded fins sprang out as the deployment springs released them. The rocket motor ignited, and the missile began its acceleration toward intercept speed. Command updates from the phased array arrived continuously throughout the flight, correcting the missile's trajectory as both the missile's position and the target's position were continuously remeasured. The antenna accomplished this by electronically directing its beam first at the target to measure its current position, then at the missile to measure where it was and what corrections were needed, then back to the target, cycling between these functions fast enough that neither tracking task was meaningfully interrupted by attention to the other. The computer integrated the 2 streams of position data and transmitted the resulting correction commands to the missile's control surfaces. The engagement envelope of the initial version covered targets from 10 meters altitude, barely above the treetops, to 6 kilometers, at ranges from 1.5 to 12 kilometers. This low-altitude boundary was the design specification that had driven the entire program, the capability gap that existing systems had not addressed, and the system met it. At the upper end of the speed range for which the system was designed, targets moving at around 700 meters per second, the effective engagement zone was smaller, but within that zone the performance was adequate for the mission. The designers who accepted the system into service in 1986 were already planning its successor. This was not unusual in Soviet military development practice. Systems were routinely designed as platforms for evolution rather than as fixed-point solutions. But in this case, the planning was driven by specific operational experience and specific identified limitations rather than by abstract ambition. The most significant operational limitation of the initial version was that it required the vehicle to be stationary to fire. This was a deliberate design constraint, accepted because the alternative, accommodating the motion compensation required for accurate engagement while the vehicle moved, was technically too difficult to solve in the time available. But the tactical consequence was real. A system protecting an advancing armored column from air attack had to stop, deploy, engage, and then remount to keep pace with the formation it was protecting. In a fast-moving operation, this created windows where coverage was absent and created predictable delays that a sophisticated adversary could potentially exploit. The modernized version that was developed through the late 1980s addressed this limitation along with several others. The new chassis was heavier and more capable than the original, reflecting the additional weight of the improved electronics and the additional systems that were being integrated. The crew was reduced from 4 to 3 personnel, with the automation systems absorbing the functions that the 4th crew member had previously handled. The computation architecture was substantially upgraded, and the system's ability to be networked with other air defense elements, sharing targeting data, receiving assignments from higher command echelons, contributing to a common recognized air picture, was significantly enhanced. The target detection capability doubled. Where the original version had processed up to 24 simultaneous contacts, the modernized system handled up to 48. The processing improvements also addressed the passive jamming problem, the use of radar reflective chaff dispensed by an aircraft to create false targets and confuse tracking. The new signal processing architecture could distinguish between genuine aircraft returns and chaff clouds automatically, without requiring the operator to perform the analysis manually, maintaining track on the real target while the decoy cloud dispersed. An optical tracking channel was added alongside the radar, providing the ability to track targets in conditions where radar jamming might otherwise have degraded the tracking quality. By measuring the target's angular position optically and combining this with the radar's range measurement, the system maintained accurate tracking even when active jamming reduced the radar's angular resolution. The combination of two independent tracking methods made the system substantially more resistant to the electronic countermeasures that Western tactical aircraft had been developing specifically to defeat Soviet air defense radars. The missile that equipped the modernized version was physically almost identical to its predecessor in dimensions, a necessary constraint because the launch containers and the overall vehicle architecture had been designed around specific dimensions, and changing them would have required redesigning most of the vehicle. But within those external constraints, the propulsion, the warhead, and the guidance electronics were all improved. The faster motor increased the missile's maximum speed. The upgraded warhead improved lethality against hardened targets. The enhanced guidance electronics improved accuracy, particularly against the small, low observable targets that represented the most demanding part of the engagement envelope. The probability of kill improvement was most dramatic against cruise missiles, the category of threat that the entire program had originally been motivated by. Against that target type, a single missile from the modernized system achieved hit probability figures that were substantially higher than those of the initial version, reaching levels that made two missile engagements of single targets largely redundant under most circumstances. The system was achieving against its most important target category the kill probability that two missiles from the original version had been required to achieve. The version that added firing on the move capability represented the most significant tactical improvement since the original system entered service. Achieving accurate engagement against airborne targets while the vehicle moved required compensating for the vehicle's own motion in the targeting calculation, maintaining stable antenna pointing against the vibration and pitch and yaw of cross-country movement, and solving the geometry of an intercept where the launch point is itself moving. Each of these problems required engineering solutions that had not existed when the original system was designed. The capability, once achieved, changed the tactical relationship between the air defense system and the formations it protected. A system that could engage threats while moving at road march speed could maintain continuous coverage over a moving column rather than providing intermittent coverage during the pauses required to deploy and redeploy. The tactical geometry of protected movement changed when the air defense element was no longer a constraint on the column's speed and could instead keep pace with the armor it was covering. The missile that the full second-generation system carried represented a genuinely significant advance beyond what had come before. Smaller and lighter than the previous weapon, despite carrying more capable propulsion and a more effective warhead, the new missile enabled a doubling of the vehicle's ready ammunition from 8 rounds to 16. 16 missiles on a single combat vehicle, a ready load that no comparable system in any military had previously approached, meant that the system could engage multiple simultaneous threats, absorb a saturation attack, and still have remaining capacity without the delay of reloading. The range and altitude improvements were proportional to the propulsion improvements. Maximum engagement altitude roughly doubled. Maximum range increased significantly. The speed of the improved motor extended the effective engagement zone against fast targets. And the guidance improvements pushed the probability of kill figures against the most demanding target types to levels that the designers of the first version would have considered aspirational. The commercial quadcopter drone problem, which was not anticipated in any form by the engineers who conceived the original system in the 1970s, revealed itself as a genuine operational challenge during the system's later service life. Detecting a small commercial unmanned aircraft, a device weighing a kilogram or two with a radar cross-section smaller than a large bird, at operationally useful ranges required radar sensitivity and processing capability that represented the current limit of what the technology could achieve. The system could detect such targets. Whether it was appropriate to engage them with a missile costing orders of magnitude more than the target itself was a different question. And the operational answer that emerged was to use the system's detection capability to locate and track small unmanned vehicles and pass their coordinates to other, cheaper weapons. The radar became a sensor in a layered engagement system rather than the engagement system itself for this target category. The modular variant, the combat system separated from any specific vehicle and made available for installation on different platforms, including wheeled vehicles for customers who preferred them, or static mounts for the protection of fixed installations, reflected the maturity of a program that had evolved far enough that its core technology was worth separating from any specific chassis configuration. The combat module retained all the engagement capability of the vehicle-mounted version. It could be installed on a wheeled military transport for customers whose terrain and logistics made tracked vehicles impractical. It could be placed on a static mount to protect an airfield or a fuel depot. It could be lifted by heavy helicopter to a position that no ground vehicle could reach. The evolution from the original 1986 system to the current versions spans 4 decades of continuous development, and the technical distance traveled is substantial. The search range has grown. The engagement altitude has grown. The number of simultaneously trackable targets has grown. The probability of kill against every target category has grown. The ready missile load has doubled. The ability to engage while moving, which the original version explicitly could not do, is now a standard characteristic. The ability to network with other systems and operate as a node in a wider air defense architecture rather than as a standalone platform has transformed the tactical employment options available to the units using the system. What has not changed is the fundamental architecture, the single vehicle concept, the vertical launch, the phased array guidance, the integration of all functions into one autonomous fighting machine. These choices were made in the early 1970s, validated over years of difficult development, and have proven robust enough to accommodate 4 decades of technology evolution without requiring replacement. The engineers who sat in their offices in 1972 and described what they wanted to build, knowing that the technology to build it did not yet exist, were right about the concept. They were right to wait for the technology rather than compromising the concept. And the system that eventually emerged from that patience has demonstrated, through successive generations of development and through operational use in multiple conflict environments, that the foundational judgment they made was correct. The war in 1973 that set the requirement is half a century past. The specific aircraft types and missile systems that defined that conflict's air defense environment are museum pieces. The system that the Soviet engineers began designing in response to those lessons is still in production, still in development, and still in service.